I mean, day and night at any time, you can look anywhere. The sky is dark. There is no atmosphere. There is no disturbance. Even the largest telescopes on the ground will have some disturbance due to the atmosphere, due to thermal effects. Such a big steel structure, there will be expansion, contraction, temperature changes are there. A lot of engineering goes in to keep the temperature cold. Finally, in the night, you have to open the dome and the telescope has to look out. No, you can't keep it closed. So there will be some limits. So space is that way much better. Now you see, for some reason, see, the Earth is getting in the way. Sometimes, so in space, if you go far enough out in space, no, if you go far enough out in space, see what is blocking you here is the Earth, ground. If you go far enough out in space, not immediately around the Earth, far enough, then even the ground won't be there. Okay? So you can look in all directions, up, below, everywhere you will see stars. So there are some missions and instruments which go quite far from the Earth, quite far from the Earth. So okay, we can close this for now. So Hubble Space Telescope, which is the same size as the telescope we have at our observation tower, 2.3 meters. But its images are beautiful because the resolution is superb. It images at the diffraction limit. Okay. Another advantage in space is there is no gravity acting. I mean, lesser gravity is acting there compared to on the ground. The acceleration due to gravity will change with time. And if you go far enough out in space, in fact, Hubble still has some action. If you go much further out, there is no gravity. So if you put two mirrors like this, just connected by thin elements, there's nothing will cause the bending of the structure and all this kind of thing won't be there. Here also, most of the gravity is reduced because it goes around, right? The very reason something goes around in orbit is the centripetal acceleration, centripetal force due to this rotation equals the gravitational force. So most of the gravity force is eliminated. So you don't need such a large structure. So the optical elements to keep them aligned. So the imaging, those effects are also highly reduced, those bad things. So the image quality is superb. Okay? Sometimes you can have perfect optics. At the moment you have the telescope vertical, it is fine. The moment you make it horizontal, this whole thing can bend and disturb the alignment of the optical elements. So there are many other engineering aspects. I can't unfortunately go into all that. And towards space, there is this, which has been launched on 28th September. Just now I was at mission control to see this launch. Because I and a colleague had proposed the ultraviolet imaging telescope, which is these two telescopes sitting in the middle. Okay. We started this in 1998. Finally, it has got launched. Now we have to see. Initially, they are testing the satellite. That what ultraviolet images we get from there. There are other instruments also. The rest of these instruments, these green boxes are over a X-ray range from half to 100 kV X-ray energies. It can make measurements. This is the soft X-ray imaging telescope, this green tube. This is a cadmium zinc telluride detector array for very high energy X-rays. So this is completely dedicated to astronomy, as to send. A lot of interesting things there, but I can't really go into it. This is some description of what I just told you, those various instruments. And on the right is what we built at our institute, these twin telescopes. You must imagine in orbit there are a lot of issues there. Space qualifying any of these instruments is very difficult because there is a range of temperatures. You go around, this is a near Earth orbit, 650 kilometers altitude above the Earth. So atmosphere is all below, so atmosphere doesn't affect you. But still, there are disadvantages like when you come on the day side, one orbit is about 98 minutes. When you come on the day side, the sun full heat comes. See, the atmosphere does some protection from the heat of the sun also. In space, there is full direct heating and radiation as well as heat. Whereas when you go on to the night side of the orbit, it becomes very cold. So a lot of thermal cycling range is much more in this space. A lot more difficult materials have to survive. But if you are able to overcome those difficulties, the results are of course fantastic compared to what you can do with the ground. Okay, now we come to some of the elements of the astronomical objects. Of course, you know the sun and you know all the planets, sun and solar system. These show the relative sizes of all the planets. Okay. But the relative distances are not correct because it won't fit into the screen otherwise. The relative size of the sun is also correct. But you can't draw all of it because it's a huge circle. Only one part. I won't tell you more about it. You people may already know, and here are some summary properties. Important things to note are there are distinct classes of planets. These are all higher density, you can see. Whereas the rest are all much lower density. They are called the gas giants, gaseous planets. And they are all bigger. You can see the ones bigger diameter. Jupiter, Saturn, Uranus, Neptune. They are all bigger diameter. And they are lower density. Why this is important is that now a lot of planets are being discovered around nearby stars. Naturally, earlier means even till around 1980s, people thought that the Earth has planets around it, maybe other stars also have planets around it. Okay, when the stars are formed, as you will see a little later, from material, gaseous material which is there in space. And so stars are formed, and then some more remnant material which is remaining, they condense into planets. So people thought there would be. But from the late 90s, 1995 or 6, actual detection of planets has started. Okay. So we know that there are many planets. Okay. The thing is, it is difficult to measure them. And the question always arises that how far away. So if you take the relative time and the various speeds, you see how much time it will take to reach even the planets in our system, say Jupiter and Saturn. And the nearest star, which is Proxima Centauri, which is 4.5 light years away. So if you want to reach a planet there, going at the spacecraft speed, it will still take 70,000 years. So it is quite out of reach at the moment. So distances are huge. In astronomy, of course, these are details about the sun and the elements it contains. We'll come back to distances later. Important point here to tell you is that there is no other place in the universe where elements are formed naturally, except in the centers of stars. Even every atom in your body, every carbon, nitrogen, was actually made in the center of some star long ago. It doesn't get made here. Yes, please.
Sir, how you want to know about the composition of the hydrogen helium?
Because they measure it, they take a spectrum and they take the energy in the spectral line and that relative, I'm telling you in a very crude, rough kind of way, but element abundance measurements are done from spectrum. So you get the composition of those. Those will give you relative to each other. But to get the total amount, you must know the total mass of the star. That is the different issue. How many tons of hydrogen, how many tons of helium. You can convert once you know the mass of the star. These are just percentages by relative terms. Hydrogen is the most abundant element in the universe. And the universe was formed, actually, from the beginning, from elementary particles, electrons, and that first protons were formed. Okay. Once the proton is formed, and the universe cools, it captures the electron, and that's an hydrogen atom. That's how hydrogen atom is the most abundant element, because it formed first in the universe. I'm not going to be talking about the formation of the universe, because there are too many things. Okay. There are some limited vistas here that I will talk about. Okay. So anyway, the important thing is all the elements were formed in the centers of stars, okay, such as our sun. Maybe the percentages are different in different kinds of stars, and it depends also what is the generation of the star. The stars which were formed early in the universe from the primordial material would have, those are called metal weak stars. No metals have been formed yet, mostly have. At that time, I think 98, not 98, 92, little more than this, 92.8 or 93%, the early universe. Then these stars form, some of the stars form these elements, and then they blow up and throw the material away, which mixes with the available material around, and the new generation of stars is formed from that. So those stars have a little more proportion of the heavier elements, apart from that. So that's how generations of stars increase the measurement, the amount of heavy elements. No other place is there where elements are made. Except now in the laboratory, a little bit we can do. In the universe, this is the only place. And internal structure of the sun. Mind you, the nuclear fusion and formation of elements takes place only in the innermost 10%. You take by the diameter and the volume, innermost 10%. That is because an object like the sun, it is under its own gravity pressing, and it is in equilibrium. It formed out of material and it was bigger, then it contracted under its own gravity and reached an equilibrium position. So the pressure and density in the center, the temperature in the center is around 10 million degrees, and pressure is several thousand atmospheres, several thousand times our atmospheric pressure. So under those high conditions of pressure, actually several billion atmospheres, not thousands. Okay? So that high condition of pressure and temperature literally makes the atoms, the hydrogen atoms almost come and touch and fuse. Otherwise there are nuclear forces which will make them repel. Two protons will repel. They will not fuse normally. Electrically they are both positively charged. So to overcome those electrical repulsion and have nuclear forces taking over and then giving you all this, you need to have those kind of conditions for fusion of the elements to take place. And this is typically a surface of the sun. Generally true of all stars on the average. There are differences, but they are all like this. So there are things shooting out. The energy formed in the core from fusion is all gamma rays and neutrinos. They are not yellow light like this. So those gamma rays, as they come outwards, they interact with the outer material inside the sun, and they get converted. Gamma rays interact with other, ionize them, those emit further, lower and lower energy photons are emitted. Finally what comes out in the surface is what you see this surface as being of a particular color with a particular black-body temperature, which is 6,000 degrees. On surface temperature is roughly 6,000. But you are only measuring this outside, you are not directly measuring the inside. Okay. To know what is happening inside, you have to use nuclear physics and models and nuclear synthesis and all this. Okay. There are ways of measuring directly using neutrinos. There are elementary particles called neutrinos, like you have electrons. There are neutrinos are there. And neutrinos have very small interactions with matter. You take a beam of, let us say, 10 to the power of 36 neutrinos, that is 1 with 36 zeros. So many neutrinos you bombard on the earth. Only one may interact with the other, rest will just pass through without noticing it. So their interaction cross-section is very small. What is called interaction cross-section in elementary particle physics. So they are very elusive particles because you can only detect provided it interacts with the detector, right? You cannot detect the particle if it goes right through without any change. Okay. So, but now neutrinos, there are detectors, and it is mostly neutrino astronomy because a lot of neutrinos come out from the sun, it's the nearest star. Neutrinos are generated before, and they can measure them now. Okay. This year's Nobel Prize in Physics actually was given to two people who built neutrino detectors in Japan and Canada. It is Takai, Japanese scientist, and the Canadian. Everybody know the name? Anyway, you can look up the newspapers. Yes.
Is Arthur M.C. Donald.
Sorry?
Arthur M.C. Donald. The Canadian scientist.
Yes. Arthur. MacDonald. Yeah. MacDonald. Not M.C. Donald. MacDonald. So these are two people who got the Nobel Prize And their work was on measuring solar neutrinos. And they discovered that when the neutrinos are coming from the sun to the earth, about half the neutrinos change into a different kind of a neutrino. That was this year's Nobel Prize. And then these are the various planets. There are various studies in this. Let us not go into that. We are running out of time, as usual. Okay. So Mars, we have a Mars orbiter mission which is studying in more detail. It's known Mars has got polar caps. One polar cap is frozen carbon dioxide, CO2 ice. The other polar cap is water ice, H2O. Okay. And then of course there are moons in all the planets. We have one moon. Mars has two. This is Jupiter with so many moons. All of them have Greek names. I don't think we have Indian names in Indian mythology for any of the moons of planets. Okay. So I have not come across. But the Greeks named them, of course, after Galileo made the telescope, then they were named. Then if you go to the solar system, you can see the orbits of some planets written there. And then outer to that, you have much larger areas. Okay, these are all satellite. Yes, so what is the commotion there? You are tired. If you are tired, but then please don't disturb the others. Okay? So there are outer bodies and further a cloud of debris left over from the solar system, which sometimes come close to the Earth, okay, as asteroids. These are pictures taken by space missions. Okay? Or they come as comet. This is Halley's comet. This is Ison comet, which we have taken with our telescope. So this is the solar system. Then of course, for the Milky Way, sometime in the course of the last 100 years it was realized that these are all individual stars, these patches, as telescope. They were individual stars. And there were small patches seen elsewhere also, which people realized were other galaxies, like our galaxy. All the stars which you see are in our galaxy. Rest of it is all, we will leave this out. Distances somebody wanted to know. Okay, stars here. This is the relative size of stars and planets. So if you see, for example, Jupiter here is so big, and it's our sun. The other sizes of stars are so big, much bigger. They're gigantic stars. In fact, there is one star called V by Canis Majoris. It's a variable star. It's so big that it covers the orbit of Saturn, right up to the orbit of Saturn. It's merely to explain those scales. But all the stars are formed out of nebulous material. That illustrates here. They are formed out of those stars. And these are very blue stars, so they are very hot, massive stars. They form in clusters sometimes. This picture is one of our telescopes. So we will leave just a listing of the areas of kind of research which is done. And the earlier HR diagram with some more details, showing where the stars arrive at various stages in their lives. This is only to give you a feel. Okay, and here you note that some kinds of stars will blow up as supernovae. They explode at the end of their lives. Some of them will become red dwarf stars. Other stars will become black holes after blowing up, like here for example. And other stars will become red dwarfs. Slowly they will cool off over the lifetime of the universe. The various fates of the end of the evolution of stars, which happen, which I can't tell you in detail. These pictures are all about various star-forming areas, and this is the nearest stars. This is the volume where people are looking mostly and trying to study planets around these stars in detail. If there is any chance, 12 light years is the smallest of distances close to which we can think of going in maybe a couple of hundred years. So that is why I show you this. There are very few within this. Okay. And then if these are objects in the galaxy, which I will not deal with. If a star blows up, our sun will become something like this. The sun is 4.5 billion years. Another 4.5 billion years, it will throw out its outer layers. And it's called a planetary nebula. Like a planetary orbit, there is a nebula like this. The central star of the sun will become a white dwarf. Long before that, we will be dead, of course. The moment it becomes a red giant and changes its energy output, Earth will perish. And then this is just to tell you that the sun is in a system, what you call the Akash Ganga. It's actually it's called a galaxy. Again, with all the technology used and measuring the distances of the stars in various directions, this picture was. This left side is an actual picture, right side is a representation. So they conclude that about 200 billion stars are there in this galaxy, and the sun is roughly 2/3 of the way from the center to the edge. So this is one galaxy. And let's not worry. Then the other things are more like taxonomy, bulbs, disk, etc. We won't worry about it. And I told you X-ray, gamma rays, infrared. So the whole galaxy can be studied in various wavelengths. So you can connect up the physics which is occurring at various wavelength scale by connecting up the information in these images from across the galaxy from different things. Okay? A lot of physics comes out from that. As of 6th October, I was telling you about planets. There are 1,969 planets that have been discovered by a spacecraft called the Kepler mission. Okay. And why I am showing you this, and this is the property, the star, mass of the star around which the planets are on the y-axis versus the mass of the planet. They all seem to be clustered in one direction because this mission is looking for planets which might have intelligence. The question always remains, are we alone? Or are there other people elsewhere? And would we be able to communicate with them? So that is why. So there are identified, out of all these planetary searches, potentially habitable planets. Out of these, many of these almost 2,000 discovered now. And this is going on. The mission is going on. It's a very complicated method to measure this because if you see a star, you can never see like that with a telescope. There are some techniques used to do that. So if there are any aliens, as some of us like to say, probably which we can recognize, maybe different shapes, maybe some are peaceful, some are warlike or whatever, some maybe spider-like or whatever, but biologic as we understand it. Okay, these are likely places they can occur. This is done by a complicated technique, like out of the 9 in the solar system, only some range of distance has the right temperatures to have water, formation of molecules, etc. So these criteria are used to select them and then study in detail. Okay? So, and notice they are all small, much smaller than Jupiter. Reference for Jupiter is given there, Earth is given there, and that's it. So these are all much smaller than Jupiter kind of. Then of course we will not go much further, except to say that there are many faint patches in the sky which are galaxies, other galaxies. Whatever planets and stars we are studying in our galaxy, there are many patches like this in the sky which are other galaxies. And you can see there was somebody called Edwin Hubble, after whom the Hubble Space Telescope is named. He took spectra of many of these, as you see in the bottom, and the spectrum lines were shifting. So he attributed this to the Doppler effect. Have you people heard of Doppler effect? When something moves with a velocity, there's a shift. Even in the sound, you hear a railway coming towards you, the sound then shifts to high frequency. Same thing. So that versus the distance measured due to other means, he was able to conclude that these are all other galaxies which are all expanding away. So the universe has billions of galaxies, billions and billions. As I said, I'll stop here, we already late. And that is the story for another day. That's a completely different vista. And our galaxy is part 1, and we are one small star sitting in the galaxy. So there is plenty of scope for aliens all over the universe. So be prepared. Thank you. Yes? Why they rotate on their own axis? That is because both planets and stars are formed from a gaseous clump. Like in some of the pictures you saw, like cloud-like bright material, right? So all material in such clouds eventually collapses under gravity. On large scales, gravity is the dominant force in the universe. It is not a dominant force, for example, in this material or here. These are electromagnetic forces between, particles in the atom or chemical bonds in the material in your body. But large scale in the universe, gravity is the dominant force. So any large cloud of material will collapse under its own gravity force. And till the density becomes high enough, it forms a star. While collapsing, there is a spin gets introduced because there are turbulent eddies. When the Mahanadi is flooded in the monsoon, the water doesn't just flow like that. You will see eddies, whirlpools. So material tends to develop eddies while collapsing and forming stars. Those eddies means angular momentum. So that gets finally transformed to make the whole star be rotating. When it collapses, it forms a single star. Same, I am telling you very roughly, there is a lot of mathematics to it also. But that is the reason.
Those are questions you can interact during the break time. Because we are on. Thank you very much, sir, for your inspiring talk. And I hope you must enjoy the session. And many of you must have been motivated to pursue your career in astrophysical sciences. So again, sir, thank you for your valuable time. This is small to